The mass spectrum for benzoic acid is shown below. Which ion represents the peak at the m/z value of 122? So if we're looking at a mass spectrum, we should first review what's going on inside the mass spectrometer. So what happens in your electron ionization mass spec is you have a molecule, we'll represent that by M, and it's going to be bombarded by a beam of high energy electrons. So we will say an electron beam. And what this does is it's going to knock just one electron off of your molecule, which results in a molecule that has a positive charge and a lone electron. And also it frees that electron, which we're not going to see. And this here, when we have your molecule minus one electron as the radical cation, this is known as the molecular ion. And as you can imagine with a radical cation, it's not very stable. So this will usually break down further to give you positively charged ions and radicals. And it is your positively charged ions that are seen by the detector. So this is the mass of these ions that we're seeing in the mass spectrum. So the positively charged ions appear in the mass spectrum. So one really good approach is to start with the weight of your molecular ion, because your m/z value, m/z stands for mass to charge. And since the charge that we're looking at is always +1, what these numerical values are is the mass of those ions. So we're being asked to say what ion represents the peak at an m/z value of 122. That means your ion weighs 122 atomic mass units. So we can do this by weight. So where you're starting with a molecular ion, which would be the totality of this molecule, and then it's breaking down into smaller parts, a good approach would be to start by calculating the mass of your molecular ion and then see what's lost, if anything, from that ion to get this peak at 122. So what we can do is we can look at your benzoic acid. And so we have the structure. And from the structure, we should be able to calculate the molecular weight. So we can see that we have 7 carbons, 6 from this ring plus 1 here. Hydrogens, we have 1 at every carbon of the ring besides where we have the substituent. So we have 5 around the ring. I'll just draw them in so we can make sure that this is nice and clear. And then the hydrogen that's attached to the carboxylic acid. So 6 hydrogens and 2 oxygens. And if you do some quick little math here, right? 7 times 12, 12 being the weight of carbon, 6 times 1, 1 being the weight of hydrogen, and 2 times 16 for your oxygen. If you do all of this math, you're going to end up with 122 AMU. So what that tells us, right? So that's the weight of the benzoic acid itself. So this ion at 122 is the molecular ion. So if we're looking at these possibilities, what we have here in A is showing us the molecular ion. It's showing us the entire benzoic acid as a radical cation. All right. So that answers the question. We can also assign these other key peaks, and I think that's a good exercise to go through here. So if we look at going from 122 to 105, so this fragment at 105, so the difference here, 122 minus 105, is 17. So that tells you that 17 mass units have been lost. So you'd have to ask yourself, well, what weighs 17 that we can imagine readily being lost from this molecule? And what this is the loss of the OH group from that benzoic acid. So if you look at this ion C, and you were to add up the weight, this is what you'd find at m/z value 105, right? So we've just lost the OH from that benzoic acid. And this is the base peak in this. It's the peak that's at 100% abundance. So these tend to be peaks that are very stable, right? So the cation is surviving long enough to reach the detector and appear prominently in the mass spectrum. And so what makes this particularly stable is that we've got some resonance stabilization. So you can bring in these electrons from the oxygen to stabilize that cation, okay? And the other peak we have is at 77. And this is something you'll commonly see with aromatic compounds, because what weighs 77 is this fragment B. And that's because it's the benzene ring, C6, and we still have the 5 hydrogens around the ring. No hydrogen there where you have the positive charge. There wasn't a hydrogen to start with, and once you've broken that off, there still is not. So that's that C6H5. So we see that peak prominently in compounds that are monosubstituted benzene rings. This other fragment we have here, D, we would expect to see this at 1 mass unit less, at 121. And this just, it isn't appearing in the spectrum, so that's not something that we're seeing a whole lot of. Okay.